Hi, thank you so much. So I'm going to be talking about neuroplasticity and resilience, sort of taking off from what Harris was just mentioning. Next slide, please. So as he was saying, we want to preserve brain capital, and that's really critical to society, especially in the context of the COVID pandemic. I think we're understanding more and more how resilience is really important at so many levels. And brain resilience is particularly important. So we talk about resilience as the ability to bounce back. So this could be after a brain injury or the onset of a mood or behavioral disorder, or it could be in the context of a cognitive disorder that's developing in late life or a neurodevelopmental disorder earlier in life. But even beyond that, as we now know with the COVID pandemic, societies, countries are focusing on resilience, how to be more resilient in the face of a major catastrophe like the COVID pandemic. We know that supply chains need to be more resilient. There are so many levels of resilience that are now clearly important. But brain resilience is sort of the basis, I would say, for all of that. Ultimately, at an individual level, if we have individuals that are more resilient, that leads to society being more resilient. And brain resilience can be mediated through the concept of neuroplasticity, which is what I want to get into today. Next, please. So William James coined the term plasticity. So the concept here is that plastic can mold to a shape and retain the shape. So you can make a mold, it'll stay that way, it won't kind of dissolve again. And the idea here in terms of brain plasticity or neuroplasticity is that experience shapes the brain and that change is retained in the brain. Next slide, please. So there are a couple of mantras that are used a lot in the neuroplasticity world, and I'll be talking about both of these in some detail. The first one is that neurons that fire together wire together. And the second is the concept that the brain is doing tuning and pruning. And we'll get into the details here shortly. But I just also wanted to show this book here, Live Wired by David Eagleman, neuroscientist. I wanted to kind of point this out because this is a really good book talking about neuroplasticity. This is a book for the public. So really this concept of neuroplasticity and resilience has really made it into the public consciousness now as well. And I also have a book which kind of talks about neuroplasticity as well to some degree called The Traumatized Brain. So again, for the general public. Next, please. So let's kind of get into the basis of all of this, neuroplasticity. So the concept here, the first mantra I mentioned to you is that neurons that fire together wire together. And this is really coming from Hebb in the 1940s. Basically, the concept is that neurons that are firing close in time to each other repeatedly will form more connections with each other. So if there's a neuron A that's driving the activation of neuron B repeatedly, the connection between neuron A and neuron B will be strengthened. It'll be potentiated. So that's at an individual neuronal level. At a larger level, there's the concept of tuning and pruning. So that's basically the idea that there is a competition between neurons, between parts of the brain. And so the connections that are used more and more, they're strengthened, they're tuned in, and connections that are not used very much are pruned out. So this is done by experience. The brain prunes out connections that are less used and tunes into and expands connections that are more used. And this is really kind of a Darwinian competition in the brain between neurons. Next. So historically, neuroplasticity was kind of thought to be more in the domain of pediatrics, kids. It was thought in the past that adults don't have much or any plasticity, but children do. Well, that's certainly true. Children certainly have a lot of neuroplasticity, but adults do as well. And so learning involves neuroplasticity, and we do that all the time, even as adults. Hopefully right now, we're learning things. So that is kind of, that's causing changes in the brain at this neuroplasticity level. We know that there's this concept of long-term potentiation, which is thought to be the basis of learning. And really, that is kind of the same concept that we're talking about. If you have the activation of certain neurons repeatedly, over time, those neurons then have long-lasting signals. And so eventually there's learning. So learning involves neuroplasticity. Neuroplasticity can be good, such as with learning, but it can also be detrimental. Next, please. So an example of detrimental neuroplasticity is phantom limb syndrome. So this is where a person loses a limb and they still have residual sensations from the missing limb, often in the form of pain. And worse still, the pain from the limb could be felt somewhere else, such as the face, because the limb's representation in the sensory cortex has been overtaken by the face's representation. So that overtaking of representations, that's an example of neuroplasticity. We're talking about these connections being pruned and tuned, and sometimes that can be dysfunctional. Next slide. So this is just an example of a homunculus, the little man as it's called. There's both a sensory homunculus and a motor homunculus. And either case, though, the idea is that the representation of the face is close to the representation of the limb. And so in some cases of phantom limb syndrome, the loss of the limb basically means that there's less representation in the brain for the limb. And that area, that space in the brain, that representation is taken over by the face. And so people may then feel the phantom limb pain in the face, which is from the limb. So it's interesting. I mean, the brain is always changing. It's always dynamic. And sometimes that can be good, but sometimes it can actually be detrimental. Next slide. So there are technologies, though, now and methods to enhance beneficial neuroplasticity. And neuromodulation is one example of that. TMS, transcranial magnetic stimulation, and behavioral approaches. And the other way to do it is with cognitive gaming and digital therapeutics. So my colleagues on this panel are going to be talking about a lot of these things. And I'm going to be focusing for the rest of the talk on TMS. Next slide. So TMS stands for transcranial magnetic stimulation. This is a technology that is currently available that enhances neuroplasticity and can increase resilience in the brain. So it's cleared now in the United States for major depressive disorder, as well as for OCD, and as well as for nicotine cessation. So the basic concept here, what we're doing with TMS, is that we're using magnetic pulses to actually drive connectivity, to change connectivity in the brain. So specifically in depression, what we're doing is we're targeting the left prefrontal cortex, which is part of the cognitive control network. And the thought is that in depression, the cognitive control network is not able to modulate affect, modulate emotions as it should. And so the thought process is that we want to increase activation of the cognitive control network so that it can actually downregulate or appropriately regulate other areas of the brain, like the default mode network, where we have excess connectivity. So we're really literally kind of remolding the brain, as William James kind of, as we talked about what plasticity really is, the mold, remolding. That's literally what we're doing with TMS. Next slide. So we're really targeting neural circuitry with magnetic pulses. And the basic physics here behind it is that moving charges induce magnetic changes, magnetic flux, and those changes are transmitted across the skull right into the brain, and that induces voltage changes and induces neuronal firing, action potentials. And as I mentioned at the very beginning, neurons that fire together wire together. So as we do this over and over again, and by the way, TMS for depression is over and over again. We do it 20 minutes a day, 5 days a week for at least 6 weeks. So we have to do this repeatedly. But as we do this repeatedly, the neurons that are being activated, they're firing together, they're wiring together. So there's more connectivity, there are more synapses. And ultimately, as I mentioned, for depression, our goal is to get that increased connectivity between the cognitive control network and the default mode network, and in turn kind of rebalance the problem, connectivity problem that people have in depression. So over time, as we're targeting these neurons, we're forming more synapses, there's more connectivity, and it's really kind of getting to that idea now at a bigger level, not just at the individual neuronal level, but at a bigger level across the brain, we're kind of changing the balance of connectivity. So we already have this technology. It's, like I said, already FDA approved and cleared for a number of disorders. And in the future, we're going to likely have other disorders that we can target using this technology. So this is a great example of technology that's already in existence that we can use over time to kind of increase neural plasticity and build resilience.